Hello, everybody. This is a video on two-dimensional gravitational motion, potential energy, kinetic energy, and how we get orbits from that, which is an obvious next step. And where we're going to begin is, so 2D gravity is with is the same place we sort of ended, which is to say, okay, say I have some sort of rocket and it's launched at 20 kilometers per second. Maybe I have another one that's launched at 10 kilometers per second upward. What happens? Well, we already know this concept of escape velocity, that V equals V escape when E total equals zero, which is the cusp of when kinetic energy equals negative potential energy, where neither wins. In other words, it has, well, technically kinetic energy sort of wins because if it has enough to get out of the well, remember the potential energy well in the energy graph, in the energy space. Really, if we're dealing with a graph, it would be this side. Here's the potential energy equals zero, but here's a cool way of looking at it, that if you start off here at radius of the Earth or some initial R naught, wherever you are, it doesn't have to be radius of the Earth. It could be anything. We'll do examples where it's something different. Then what happens is your kinetic energy tells you how far you go. If your kinetic energy is less, then you eventually come to a stop, turn around, and come back. And I'm hoping people will show this on their graph for what you did in the homework. Obviously, if your kinetic energy is large enough, then you will keep going, right? It'll keep going. This is in the graph, and your V final will approach some asymptotic value and will never turn around. You will escape. Here you will fall back. So this is the cusp between these two. Technically, you will escape here, or the object will escape here. Escapes. So in a way, this is a greater than or equal to. If E total is greater than or equal to zero, there will be an escape. But at the equal sign, there's one little difference, which is that V final approaches zero, but it approaches it as an asymptote, and it never turns around. It actually never gets there, right? As R final approaches infinity, V final approaches zero, so it slows down to zero, but it never actually gets there. And if we solve these two together, meaning we set kinetic equal to potential, then we get negative G M M over R initial. Remember, initial potential is initial position equals 1/2 M V initial squared. Cancel the M, we get V initial, which is the escape speed, equals the square root of G M over R. Sorry, we want that to be positive because the kinetic is canceling the negative potential, right? So we get this is our escape velocity formula. We want to know this one. Add this to your equation box. Great. So we're going to solve for the escape speed of the Earth. So if R initial equals R Earth and M equals M Earth, then V escape equals 11.18 kilometers per second. You can plug those into a calculator to confirm, but that's it. And on our graphs last week, we were showing how if V initial went below this value, then our rocket does indeed stop if it starts at the surface of the Earth. Now be careful. This is for this starting point. Obviously, if I start up here, that's a different starting point. It'll be easier to escape from up here. It's harder to escape when you're deeper in the well. So we're going to do questions like that. Cool. Part two. So that was a little review. What if we move sideways at 10 kilometers per second. What happens, right? That's the question. Well, one, V initial is less than V escape, because we just saw that V escape here, if we're starting off at the surface of the Earth, is 11.18 kilometers per second. Then if I'm only going 10, then I'm not going to escape. But what happens? Now we're going to the right. The force of gravity is down. So the force is now perpendicular to the speed. So what type of acceleration is that? Well, that's turning. And we want to then review centripetal motion, centripetal force. How does centripetal force work? Well, centripetal force is if any force, it doesn't have to be gravity, it could be twirling a string, right? It could be an electric force in an atom, magnetic force, any force, right? Normal force on a racetrack, right? Or if any force moves, so if any force satisfies, I'm going to do it really the way, I don't know if this was presented this way, I'm going to do it the precise cause and effect way. So if any force is perpendicular to the velocity vector and satisfies a mathematical requirement and is such that the force net, of course, is mv squared over r, then the path is circular. One, the path is circular, and two, F net always stays perpendicular to the velocity vector. Now, if F net is greater than mv squared over r, then the force is too much and it spirals in, or it does something different, or it does a tighter. I shouldn't say it spirals in because we're going to get a different result right now. Well, the whole issue is that it would spiral in if it stayed perpendicular. So maybe take that back a second, right? It's tighter than a circle. Let's just keep it more general right now because kind of we're going to get there right now, right? So if F net is greater than mv squared over r, then we get a tighter curve. And that could either mean a spiral or we're going to get an ellipse is really what we're going to get because the force is it doesn't stay perpendicular. If F net is as F net is too small, or you can say its velocity is too small. So either F is too big or velocity is too small. You get a tighter curve. If the force is too large, sorry, if the velocity is too big, it's going too fast, or the force is too small. Sorry, I'm tripping over my words. You can rewind and try to make this make sense. This is clear. Tripping over my words, but this should be clear right here. If the force is too big or the velocity is too small, think about it. It's going to be pulled in a tighter circle. If the force is too small or the velocity is too big, v is too large, then what? It's going to be a looser circle or a more open circle, sorry, or more open curve than a circle. So we're going to compare it to the circular motion. So to get the perfect circular balance, so first of all, we have two velocities that end up being important. There's the escape velocity, where we're looking at the energy, and now if we get a tangential motion, so this is called tangential, whereas straight up was radial. Right? And we're going to want to know those terms, by the way. Really important. I'll use them again and again and again. We want to establish the orbital speed, where the path is circular. Yes, we're going to talk about elliptical orbits, but I refer to the orbital speed as the circular orbital speed. Maybe we can call it v circular. I'm not used to that. I just realized that we're going to deal with things other than circular orbits, but I'll call it v orb for now. But when I say v orb, I'm referring to a circular orbit. Circular orbit. So that, of course, occurs when the force is equal to mv squared over r. This is a mathematical balance of force and velocity, not too big force, where it's too tight, not too loose, where it's more open, but a perfect mathematical balance, geometric balance between those vectors. Sorry, it says mathematical geometric balance, right? And if you don't remember how this is derived, if that wasn't derived for you, maybe you can come see me. We can talk about it in a little more detail. But if that made sense to you from when you might have learned that in the past or it's connecting right now, great. All you need to know is that if this is mathematically true, then the path is circular. And in this case, our net force is just gravity. And we set that equal to mv squared over r. Obviously, we're going to plug in this. And this is absolute value, by the way, because we just need the magnitude. It's just a mathematical magnitude of force equals this, right? It's just mathematically magnitude equals this. This isn't a vector equation. It's just a mathematical scalar equation. So we just have this, one of these r's cancels, and we get v orbit equals the square root of gm over r. I did something wrong in the previous slide, and I'm sorry about that, guys. Sorry about my little mistakes today. Clearly, I forgot the 2 here. This is 2 gm over r. You might have, hopefully you did that yourself. You're like, what is Mr. Pelzer doing? 2 gm over r. And what we see instantly is that, and this is going to be really important, what we see instantly is that the orbital speed, sorry, the escape speed is root 2 times the orbital speed. So v escape is square root of 2 gm over r. V circular orbit, that's a circular, is square root of gm over r. What is the difference? It's only a root 2 difference. That's kind of remarkable. I kind of want to sit with that a little longer, but I'm just going to mention it and say that's a really good thing to know, which means if you're moving at v equals v orbit, you're not escaped because you're in orbit. You haven't left. So if we want to calculate this for the surface of the Earth, right, we plug in square root of 2, square root of gm over r, right? And we get the orbital speed, right, is going to be, I'm sorry, I'm just going to calculate it again just to make sure I'm right. That's right. It's about 7.9 kilometers per second. So from the surface of the Earth, the orbital speed is 7.9 kilometers per second. So nothing orbits at the surface of the Earth precisely, but the radius of the Earth is 6,400 kilometers. The International Space Station is only 100 kilometers or so. I think it's actually, is it 100 or 400? I think it's 400. Sorry, 100 kilometers is the boundary of space. That's the length of the atmosphere. I think it's about 400 kilometers is the International Space Station. That's what, 1/16th of the radius of the Earth. So if we plugged in 6,800 kilometers into r, we get something a little, so if this is a bigger number, this will be smaller. I think the speed of the International Space Station is around 7.8 kilometers per second. Obviously, we could plug that in. This would be r naught equals 6,800 kilometers. The International Space Station, right, almost is this speed. It's almost orbiting at the surface of the Earth because the distance to space is very small. There's obviously a lot of gravity in space. Only gravity is in space, right? Gravity is holding the moon. We can calculate the velocity of the moon from this. What is the orbital speed of the moon? We could plug in that value. Gravity decreases. The orbital speed of the moon isn't as fast because r increases. So as r increases, v orbit decreases. Also, v escape decreases because we're more out of this well. You can remember, you can think of this as a well. Here's the force. Force is the slope. So here, v orbit decreases and v escape decreases as r increases, because v escape increases because we don't need as much energy to get out. V orbit decreases because the force decreases. Two different things. I said that verbally. I hope that makes sense, though. It's kind of important. V orbit decreases because of the slope, the force. Maybe I'll connect that here in this little diagram. Here, the force. Yeah, this is force. Yeah, it'll stop you. Let me make that a little more clear. Here, the force decreases. Thus, v orbit decreases. And the escape decreases because the initial kinetic energy required to be greater than the initial potential energy. The initial potential energy is less negative, so you don't need as much initial kinetic energy to escape as you go farther away. So the moon, it's easier to, the moon, if it had a rocket, could escape easier than the International Space Station. If you're the James Webb Space Telescope, which is way out here past the moon, and it for some reason needed to escape the Earth, it's easier to escape farther away. And also the orbit of the moon and the orbit of JWST is slower than the International Space Station because the force is less. It's easier to escape, right? Because it's more out of the well, and it's going slower because it is less force. I hope that made sense. Those two things are kind of important, right? So I actually want to plug it in. So let's see. I went from 6,800 kilometers to, we'll call it 380,000 kilometers. I'm going to do a ratio. This is the radius. This is the orbital radius of the moon, not the radius of the moon, but the distance from the Earth to the moon is 380,000 kilometers on average. So let's do 380,000 divided by 6,400. So it's about 60 times the radius of the Earth, which means R naught is times 60, which means V orbit is times 1 over the square root of 60, because look, that's a 6. V goes as 1 over the square root of R. V orbit goes as 1 over the square root of R. So therefore, we just multiply 11.18 divided by the square root of 60. And we get that the velocity of the moon is 1.44 kilometers per second. So velocity of the moon around the Earth is only 1.44 kilometers per second. That is pretty slow and pretty fast. And it takes 30 days to orbit. 28 days, actually. If you calculate the circumference, right, distance divided by 28 days, you should get this value. And it perfectly corresponds with the force of gravity from the Earth. I think that's pretty cool. So this inverse proportionality is pretty cool to know. This concept of as R increases, you need less energy to escape, and there's less force. So there's less force and less kinetic energy as R required kinetic energy to escape as R increases. Hope I repeated that enough. Take note of that as you will. So cool. Now we're talking about orbital things as escaping. The moon has not escaped the Earth. It's orbiting the Earth. So now I kind of want to go back to this diagram and look at what happens. So this is our final sort of analysis. Here's the Earth, mass of the Earth, right? And radius of the Earth. I actually want to start at some arbitrary R naught. And the reason I want to is because if we start at the radius of the Earth, actually, I want to start at the radius of the Earth because we actually get a really cool, interesting result. And I'll show you in a second why I wanted to, at first, not start at the radius of the Earth. So I'm going to start at the radius of the Earth. I'm going to do it this way. Remember, downward is inward, which is a trippy effect, a trippy realization. Gravity points inward toward the center of the Earth. So if you're standing right here in, Argentina, Australia, New Zealand, South America, gravity, you drop something, will point this way. North Pole this way, New York this way. So if I'm sitting here and I'm launching a rocket sideways, which would be hilarious on a launch pad if it was sideways. But if you notice, rockets when they launch do teeter sideways because the rockets can steer like a rudder. They tilt ever so slightly, and that gives them an ever so slight angle, which puts them into orbit. Because obviously if they don't want to escape, they don't want to fall back down. So instead, to not escape, but also not crash, you can orbit. So if I have some initial velocity, say 10 kilometers per second, and I have a force pointing inward, force of gravity pointing inward, then what happens? Well, I have velocity this way, force this way, it's going to turn. But as it turns, the force also still points inward. So the question is, does it go in a circle, a tight curve? We're going to see in a second it's an ellipse, or an open or more loose curve. Less tight. In other words, more open than a circle. Or escape. These are our four options. And if it does escape, what's the shape of the path? So what we get is if I have V equals V orbit, which in this case, at the radius of the Earth, which we said is a little absurd to have something actually orbit at the radius of the Earth. It would crash into buildings or Mount Everest, but you can imagine maybe something doing that, something going crazy fast sideways, and it just orbits around. It's actually falling around the Earth. And so what we're going to get is this remarkable truth. I'm kind of leading to somewhere that if V orbit is what, 7.9-ish kilometers per second, it's going to orbit in a perfect circle. If it's greater than it, remember, it's going too fast. But this is also less than the escape speed. So our V initial here at 10 kilometers per second, we're going to analyze this. V initial is less than V escape, but it's greater than V circular orbit. Which means we have an open curve. It's this one. We have a more open curve, which means it's not going to circle. It's going to kind of go like this, which means that the force isn't enough to turn it into a perfect circle. And the force eventually gets to a point where it's going like this, and it's going too fast. So the force is actually trying to pull it back. You see that? So it's going at an angle now where the force is trying to pull it back. So now we have a situation where the velocity is like this and the force is like this, where the force is actually going to slow it down, which makes it not escape. So we have a component of force that is against the velocity, and we have a component of force that is perpendicular to the velocity. Another way to look at it is that this is all radial, whereas the velocity is also in two components. The velocity is in a component that is part tangential and part radial. So we have a V radius and V tangent. Right? So the force is causing it to turn, but also there's a component that's pushing it away. but the gravity is opposing this one. Because remember, if it's going away from the Earth, gravity is going to pull it back. So both of these show us that it's going to slow down and turn. So this is going to slow it down. This is going to turn it. This is going to be slowed down. This is going to turn. Slow down, turn. Take your time and draw these separately. I kind of cluttered this diagram, but this is accurate, what I'm saying. I hope this makes sense. So this is slow down. You can either look at it as this is slowing it down and this is turning it, or you can look at it as components of the velocity. You don't have to do both at once. It's either or. It's either or components of the velocity make sense, or the components of the force make sense of it's slowing down and turning. So what's that going to look like? So we could sit here and do a precise vector analysis the entire way. And if you're at that point in your mind, you're exactly where I want you to be. But ultimately, this ends up being hard to do, as you might imagine. That if we're sitting here doing a precise analysis, right, of the precise vectors, it's going to take a while. So what we can do, first of all, is have a computer simulator do it. Or what we can do is look at really cool energy and angular momentum equations, which is what we're going to do tomorrow. We're going to prove this tomorrow. But all I want to do today is present you with this. That if V is less than V orbit, circular, you get a tight ellipse that is small, smaller than the circle. If V equals V orbit, you get a circle. At, smaller than circle at R naught, circle at R naught. Because you have some R naught, right? We're going to want to have that R naught be in space in order to have the tighter ellipse, but I'll show you what happens in a second. It's going to blow your mind. I hope it does. V greater than V orbit, but less than V escape, we get a more open ellipse, larger than circle R naught, larger than circle R naught. And obviously, if V is greater than V escapes, it escapes, but it does what's called a hyperbola. And what's interesting as a side note is if V equals VSC, it also escapes, remember, and it's a parabola. So be careful. I kind of want to hide this one because this parabola is different than the parabola you're used to. The point is the parabola we're used to in physics 1 doesn't actually exist. That if I launch at V less than V orbit, like V initial equals 4 kilometers per second, that's pretty fast. If I threw something sideways at 4 kilometers per second, it would go in a tight ellipse, and if it could go through the Earth, it would go like this. On the surface of the Earth, let's blow this up. Right? Let's look at this a little more closely. I'm going to zoom out. Or zoom in. Right? On the surface of the Earth, which is curved, what you might see, or what you would see, is something going sideways and crashing into the surface of the Earth like this. But it went so far, it's actually following the curvature of the Earth. This is part of an ellipse. Whenever you throw something sideways, gravity is not constant, 9.8. It's tight. Remember, it's slightly different depending on your radius, and the Earth is technically curving. Although that doesn't really matter that much. More importantly, the GMM over R squared is what matters most. So never are the parabolas of projectile motion actually parabolas. They're actually just a tip of an ellipse. What? There are no parabolas. Unless you're going into space in a parabola. So I'm saying I want to be careful with this one. It's different. This is a different parabola, right? So the tip of this is not a parabola. We're dismantling all of these assumptions, right? Gravity is not constant, G not constant is really the main thing because Fg equals gmm over r squared, right? Tells us that it's slightly changing, so we get an ellipse. I think that's cool. Now, if V equals V circular, let's do a little full analysis here. So let's pretend things can go through the Earth, that the Earth is invisible or something. We have some initial radius. This is V less than V orbit. This is V equals V orbit, where it would just make it around. That's kind of fun to imagine, something orbiting at the surface of the Earth. This is V, maybe I should do different colors, but I'm not. Yeah, I'm going to do different colors. Let's do blue. Light blue for this one. So this inner red one is V orbit, sorry, V less than V orbit. Here's the center of the Earth. The one outer red one is V greater than V orbit. Notice this is tighter than a circle. This blue one is V greater than V orbit, but still less than V escape. And of course, V escape will do in green. This is going to be what's called a hyperbola. And we'll go into more detail in a minute. Now, this will always be the case no matter what the initial launch angle is. So I have these launch tangential to the Earth, so we do want to be careful. Here's the Earth. This is tangent, tangential. This is radial, whether it's up or down, left or right. So we are dealing with, think of spokes of a wheel or the tangent of a circle. So at every point in space, like right here, point A in space, where's the radial vectors? There and there. Where's the tangent vectors? There and there. So we're in a coordinate system where we want to draw tangent and radial. Tangent, am I doing it? Yeah, I got it. And radial, right? Radial, tangent, tangential. So we want to think about, is it moving radially or tangentially? And of course, the force is always radial. No matter where we are, Fg is always by definition radial. But now we're dealing with more than one component of this velocity, where the velocity could be a combination of the two. I'm hoping to find a vector system that works for you guys, but I do want to know I'll be using this one. I'll be using these words. So here is our little map. Let's add one thing to it. For these three, E total is less than 0. For V escape, E total is greater than 0. And then we'll do the middle orbit where V is escaping. V equals VESC. This is a huge parabola in space. Careful, different than the parabola on the Earth, right? And E total equals 0. So that's it. Here's our map, guys. We're done. That was a lot. I hope that made sense. Rewind it. Apologies for any confusing things, but that was so good and thorough. I want it to be more thorough than just summarizing too simply. Cool. Oof. Orbits are fun. Hope that made sense. See you guys in class.